All right, here we go. So I think we are going to finish this chapter today. There's only two topics left. The first one is about something called moment generating functions, or MGF for short. And then we'll get to the last topic, which is the last distribution, called the negative binomial distribution. So that's what I've got planned for today. Obviously, if we don't finish today, it'll carry over into Sunday. But let's just jump right into the MGF idea. MGF is a very specific type of expected value, and we have that expected value written right here. So the MGF, or moment generating function, of a random variable x at t is the expected value of e to the tx. So from here, what this essentially means is, in the discrete case, this is going to be the sum of e to the tx, because remember, you always have the expected value of what goes inside your sum times the probability of x, which is your PMF. So this is going to be used in order to calculate MGFs. And MGFs are going to be really useful because, as the name suggests, moment generating functions, they could be used in order to compute moments. You've already seen one moment, such as the mean. That is your first moment. The second moment is related to variance, and not quite, but it's part of it. And then what you see in the middle section here is that if you take the derivative, so I'm looking right, I'm looking right here. If you take the derivative of the moment generating function and you evaluate it at 0, you get back the expected value of x, which is mu. If you take the second derivative, which is the next line, and you evaluate that at 0, you get back the expected value of x squared. Now that's important because recall that the variance is the expected value of x squared. So it's the second moment minus the first moment squared. So using those first two lines, you could get your mean and your variance as long as you have or know the MGF. And if you needed more moments, the third, fourth, fifth, you just take that number of derivatives. And so the rth moment is going to be the rth derivative of the MGF evaluated 0, and that's going to give you e of x to the rth power, which is your rth moment. So that's what's happening in the middle section there. It's just kind of laying out how you get your first, second, third, fourth, and so on, any moments that you might need. We're going to get to practicing that and also even just deriving MGFs in the rest of this handout. So let's take a look at the first one here, which is derive the MGF of a Poisson distribution. So that means that we want m sub x of t, which by the formula, this is e to the tx times the PMF of the Poisson, which is e to the negative lambda times lambda to the x power over x factorial. Remember, for the Poisson distribution, that x goes from 0 upwards. So there's no limit. So we want to figure out the MGF, which means we're going to need to manipulate this. I see that we have two exponential functions, and so I want to figure out, is there something I can do with that? Even though we could multiply them and bring the two powers together, I'm going to view that exponential a little differently. And I'm going to do that like this. So e to the tx is equal to e to the t to the power of x. And I put it in that form because I happen to know what I want to do is I want to bring the lambda and the e to the t term together because they share the same power. So I'm going to rewrite this as e to the negative lambda times lambda e to the t, that quantity to the x power, all over x factorial. So this is, it's getting there. We've almost got an appropriate part to this. So lambda appears to be lambda e to the t. That seems to be our form. Now what I want to figure out is where might I go from here? It would be great if e to the negative lambda were actually e to the negative lambda e to the t. Is there a way that I could, in a mathematically sound manner, do that? Any ideas? Let's see if the power, or not power, the product of one trick happens to work. So we have e to the negative lambda e to the t over e to the negative lambda e to the t. There's our 1 times e to the negative lambda e to the t, that to the x power over x factorial. So the first line and the second line are equivalent. All I did was multiply by 1, so that doesn't change anything. And what I notice is that this term times this one divided by this one, that is a Poisson distribution because it has e to the negative some parameter value. My parameter is more complicated than just lambda here. It's lambda e to the t times that parameter value to the x power divided by x factorial. What I also notice is that these parts that I'm highlighting in yellow are not dependent on x. Remember that my summation here is all with respect to x. So anything that doesn't depend on x can come out, which means that this is e to the lambda e to the t minus lambda. I just combined the two yellow exponentials times the sum of e to the negative lambda e to the t times lambda e to the t all to the x power over x factorial. And since, as I stated before, what's inside this summation is a Poisson distribution. It has the form of a Poisson distribution where lambda, or I'll say lambda star, is lambda e to the t. So this is e to the negative lambda star times lambda star to the x power all over x factorial. And what do you know the sum of all the probabilities is for a discrete distribution?
One.
One, yeah. Which finally leaves us the answer, which is e to the lambda. Lambda tends to be factored out, so we've got e to the t minus 1. And this typically is how you will see the MGF of a Poisson distribution written. We're going to do more, but let me just ask, it's the first one that you're seeing this applied to. Any questions on this particular example?
Wait, why is that equal to 1 again?
Because it is a Poisson PMF. And when you're summing up all of the possible x values when you're summing up the PMF evaluated all possible x values, in order to be a valid distribution, which it is, we know way back here, number 2, that the sum of all probabilities must equal 1.
Wait, can you go back again?
Yeah.
Okay, so I thought that's only if like you because the Poisson distribution equation has lambda to the x, but then you have lambda times e to the t to the x. So
yeah, and so e to the t is just some quantity. It doesn't matter what that is. T is going to remain the same because this is a function m of t. And so that's why I said lambda e to the t you could view as just lambda star, which means what you have is something of this form. And that is the form of your Poisson distribution.
okay.
It's just where lambda star is lambda e to the t.
Okay. Right.
All right, let's look at another. Hopefully things start falling into place. Let's take a look at number 2 here. It says if x has the MGF that is given here, then state the probability model corresponding to this moment generating function. So remember, recall that m sub x of t is given by the formula sum of e to the t x times p of x. And so when you look at this, I could see that there's an e to the t times 1, there's an e to the t times 2, there's an e to the t times 3. And so I could see from this MGF that the possible x values are 1, 2, and 3. Because that's what t is being multiplied by in the power of each exponent or exponential. But I also can see that each exponential is multiplied by a fraction. And that fraction, based on the form of this formula that I wrote on the left side there, has to be the corresponding probability. So when x is 1, that means p of x is 1/2. When x is 2, p of x is 1/3. And when x is 6, p of x is 1/6. So let's say I'm uncertain. I want to check, is this a valid model? What might you look at?
If the probabilities add up to 1.
Awesome. So I want to check if this is reasonable. So I'm going to see if the sum of the probabilities is 1, and we've got 1/2 is 3/6. 1/3 is 2/6. So I'm getting a common denominator. 1/6 is as is, which is 6/6, which is 1. So it works out. And this table corresponds to our probability model. That's the answer that it's looking for problem number 2. Questions before we move on to number 3? So this one, unlike the first one where we were deriving the MGF, here you were working backwards, going from the MGF to what is the distribution. This one doesn't have a name. You know, it's not like a well-known distribution such as Poisson or binomial, and we were able to describe it through a table like this. All right, just checking the chat area. All right, let's look at number 3 then. So number 3 says, consider the MGF that is given here. E to the t over 2 is the numerator. 1 minus e to the t over 2 is the denominator. T has to be less than the natural log of 2. So that's all given here. And we want to compute the mean and the variance of x. So now we're going to make use of what I've got in gray here. We're going to take derivatives in order to get the first and second moments, because that's what's needed in order to get the mean and the variance. All right, so let's work on getting the mean. So mu is going to be given by d dt. Let me just point out, again, the derivative is with respect to t, not x. So d dt of the MGF. And when we get that, we're going to evaluate at t of 0. And it's always going to be 0. It's not a subjective choice. It's always evaluated at 0. How do you take the derivative of this m? What would you do? What derivative rule would you make use of?
Product.
So you could rewrite it as a product, which would also require chain rule. I think there's a better option. Product would work. Anyone have a second choice? We have
The division one?
With, yes.
A quotient? Yeah.
Perfect. Yeah. So quotient rule is in my opinion, the easier route. If you wrote it as a product, your denominator you'd rewrite as 1 minus e to the t over 2 quantity to the -1 power, which is why I said you'd have chain rule in there. And it's fine to do it that way. I think it's the harder path. I'm going to do this from the quotient rule perspective. And I'm going to say how I do it. I don't know if you may have learned a little differently, but if you know it your way, then great. So I tend to think of it as low derivative high. So 1 minus e to the t over 2 is my low. The derivative of the top is still e to the t over 2. The derivative of e to the t is still e to the t, minus high, which is e to the t over 2, times the derivative of low, which is negative e to the t over 2, all over low squared, which is 1 minus e to the t over 2 quantity squared. And so this is the derivative, which you could either simplify or you could evaluate it at 0 right away. You know, either path is fine. We're going to need to simplify anyway, but we could just jump to this. When we evaluate it at 0, you are going to get 1 minus 1/2, which is 1/2. E to the 0 over 2 is 1/2 minus 1/2 times a negative 1/2 over 1 minus 1/2 quantity squared. So that's going to be 1/4 minus 1/2 times negative 1/2, which is 2 negatives, so it's going to be plus 1/4, over 1 minus 1/2, which is 1/2 squared, is 1/4. So we've got 2/4 on top divided by 1/4 on the bottom, which comes out to what?
2.
Hmm? And that's our mean. It's not always pretty. You know, you could have 2.73 and that's fine, but this problem happens to work out nicely. So I know we're going to need to take the derivative again, which is why I said now that we have the first derivative, it's going to be advantageous to simplify before we take another derivative. So I'm going to do that here. M prime, as I work through, I see e to the t over 2 minus e to the 2t over 4. I just distributed the e to the t over 2 from on top in the top left, minus, well, that's going to be plus e to the 2t over 4. And I see that cancels out nicely. You still have the same denominator. And so here we've got a nicer, an easier function to take the derivative of, because now we need m double prime. So let's go ahead and get that. M double prime of t evaluated at t is 0. This is going to give us our second moment. And so I'm going to use quotient rule again. So low d high minus high d low all over low squared. And let me just check that I didn't make a mistake. So low squared minus or times high, low d high, derivative of high is e to the t over 2 minus high. D low is quotient rule, so you bring the 2 down, rewrite the inside, take the derivative of the inside, and yeah, all right, that looks good. And there's no need to simplify this one. You can, but you're likely to make a mistake. I would say just evaluate it here and try to simplify it. So we want to evaluate this at t is 0. And when you do that, we get that the second moment, e of x squared, is going to be 1 minus a half, which is a half squared is 1/4, times 1/2 minus 1/2 times 2 times 1 minus a half, which is still a half, times negative 1/2. Divide all of this by 1 minus a half to the 4th, which is 1/2 to the 4th, which is 1 over 2 to the 4th, which is 1/16. And now we could start simplifying. So this is going to be 1/4 times 1/2 is 1/8. I've got 2 minus signs, so this is going to be plus. You've got 1/2 times 2 is 1, times a half times a half is 1/4, all over 1/16. And so when you multiply the top by the reciprocal of the bottom, you're going to get 2 plus 4 equals 6. And that's used because, again, sigma squared is the second moment minus the square of the first. So we know that the second moment is 6. We got 2 to be the first moment, square that, so 6 minus 4 still comes out to 2. So the mean and the variance for this problem happen to be the same. Again, it's not required to be that way, but it works out in this case. All right, so we've done 3 distinct types of problems so far. Let me just reiterate them once more. In the first one, we derived an MGF from scratch, and we did that for the Poisson distribution. We had to make a trick in this example. Not all derivations are going to require the trick of multiplying by 1, which I have in the second line there. But we did that, and that helped us to solve it. In the second one, we were given the MGF, and we had to work backwards in order to figure out what the PMF is. Again, it wasn't necessarily from a named distribution, so we were able to answer it through a table. That's called a probability model, a table that lists all of your observations and all of the corresponding probabilities. In the third one, we were also given an MGF, but this time we didn't need to figure out the distribution. We had to use that MGF in order to figure out the mean and the variance of the underlying distribution. Questions on any of the first 3 that we've gone through?
Oh, you know, number 3.
Mm-hmm.
I don't know. It was kind of like confusing. I know there was the equations on the top, which showed the derivative, like something like that, of the MGF. I don't know if we're using that because I don't understand why we kept taking the derivatives and stuff.
Yeah, that's exactly what we're using. So what I have highlighted in gray says that if you want the mean, which is the first moment, you need to take the derivative with respect to t of the MGF, because remember the m of t function is e, the expected value of e to the tx. And then you evaluate that at t is 0.
And then the variance was the second equation?
The variance stems from the second one. The second one gives you the second moment, the expected value of x squared. And that's why I wrote here how the variance uses the second moment. So we got the second moment, and then you had to subtract the square of the first moment, which is the mean, in order to get your variance.
Just to clarify, the mean is the first moment and the variance is the second, right?
The mean is the first moment. The variance uses the second moment.
Okay.
Moments are, so these are the moments. And the variance uses the second moment minus the first moment squared. Does that clarify, or is there something still fuzzy about which are the moments and which are the mean and variance? The mean is a moment. The variance uses 2 moments to get at it.
No, that makes perfect sense.
Excellent.
Thank you.
You're welcome. Were there any other questions? Again, any of the first 3 problems?
Wait, can I go back to 3 again? I didn't finish copying.
Oh, yeah. Just let me know when you got it.
Okay.
Okay. So let's look at number 4, which asks us to determine the MGF of a binomial distribution. So this is similar to 1 in terms of the process. So we'll start there. We want mx of t, which by definition is the sum of e to the tx times the binomial PMF, which is n choose x, p to the x, 1 minus p to the n minus x. So we need to see what we can do in order to try to solve this one, and x, because this is binomial, goes from 0 to n. This is not an infinite sum. And my first instinct is to make use of the initial trick that we had done where we viewed e to the tx as e to the t to the x power. and then combine that with the p term. To get here. Now, if we viewed p e to the t as, let's say, a p star, so this is just a thought. If we viewed that as a p star, it would be great if we could get this. So we want something of the form n choose x, p star to the x power times 1 minus p star to the n minus x power. So if we could get it into that form, that would be wonderful. You need to figure out, is there a trick or something we could do in order to achieve that? Let's seem to recall, what's this called? I think that's what we want to make use of, the binomial coefficient. Let me just refresh my memory. Yeah, so this is kind of an obscure one, which is why I'm demonstrating it. Oh, that's the same thing. X plus y. Like this. Okay. I want to take a look at what I've got. Let me make it easier to follow. What I have in the very top here. So the right side, that sum looks like a binomial form where y we can view as our p to the x, and x we could view as our 1 minus p to the n minus x. And so it has a form like that. And this is, I'm going to lose that. Make sure you have that, that general form in your notes, just so when I take this screen away, we could get back to it. So it's going to be the y term plus the x term to the nth power. Okay, got it. So according to that binomial formula, this sum is going to be equal to the y term 1 minus p, plus the x term, which is p e to the t, to the nth power. And so this actually managed to get rid of the summation right away in one shot. This is by the binomial formula. And it has that name. That is not the binomial PMF. So it's not the probability mass function. That's why I had to look it up. It's a separate formula, which I will put in the notes here. That is n, let's see, that's going to be p plus q to the nth power is the sum of n choose x, p to the x, q to the n minus x. So here's the relationship that that we're making use of.
Does it matter that on Wikipedia their sum went from 0 to infinity?
Oh, you're talking about the page I just had up, right?
Yeah.
It doesn't. That is only, that doesn't matter when we're working with the binomial distribution is where we're stemming from. That n is viewed as finite, because it's the number of subjects or trials that you're looking at. And so you're not just going on and on and on. And so it is, it's not viewed as an infinite series.
Okay, thank you.
You're welcome. And so if you find a table, eventually I'll give one with common MGFs. Right now we're kind of discovering them on our own. More often than not, you'll see this written as q plus p e to the t to the nth power. Remember that q is 1 minus p. So that's a more common way that it's written. This is one of the few distributions where you'd have to make use of this trick of the binomial formula. It's not a common one, which is why I'm showing it to you instead of putting it on a quiz, because it's not something I'd expect you to think up. But that's where it may be useful for to make use of it. Any other questions? We have exhausted all of the example problems on here. All right, so here I'm making a problem up. It's a valid one, but I'll just make it up here. I want to see if you're able to derive the MGF for a Bernoulli distribution. I didn't give p a value, so I'm leaving it very general. So your answer will be in terms of p and or q. And I want to see how far you're able to get. This is one of the easiest that you could go through, and the reason is because with only 2 values for x, you can evaluate the sum. There's really no manipulation other than after you state the formula, actually evaluate the sum, and that'll give your answer pretty directly. So I want to give you a minute or so to see if you're able to get this. and I'll check back in.
The moment generated.
Yeah, no, it's
The moment.
This used the it used the general definition for MGF, but in this case, we didn't have to apply any sort of trick like multiplying by 1 or using the binomial formula. You could use the binomial formula, but you're only evaluating at 2x values, so it's pretty quick and simple to evaluate and get at the answer.
I still don't get where you get x equals 0 to 1, because it didn't say that in the equation on top.
It doesn't have to, because if you go back and look at the Bernoulli and binomial handout, the top PMF is your Bernoulli distribution, and what does it say x can be?
Oh, you're looking at that. Okay.
Yeah, so that's why you know, I've tried to emphasize in words that the components for this chapter that you should really focus on are knowing the distributions, knowing when to use each, and knowing their support. And if you haven't heard the term support before, support domain, they're related. And so support for Bernoulli is just 0 and 1. For binomial, which is at the bottom in yellow there, it's 0 up through n. For Poisson, it is 0 onwards. So Poisson is infinite. For hypergeometric, it is like the binomial distribution in terms of its support. It goes from 0 up to n. And so it's really important to be aware of the support for the distribution that you need to use.
And then binomial is supported 0 to n.
Mm-hmm. Any other questions? All right, I'm just going to test out this polling feature because I never tried it before. So let me see if I could quickly add a question. All right. Okay. Okay, let's, it's my first time making use of this. Did it happen to send you guys the polling questions automatically, or is there something else I need to do?
Where was it supposed to send it to us?
I assume that a question would just appear.
No, I didn't get anything.
Oh, you sent some? I don't know.
Tried to send something.
Wait, like emails? You said like a poll or something. I don't know how that works though.
Not through Lalima. This is through Zoom. And you create 2 polls for this meeting. All right, that's great. How do I send this to you guys? Edit, delete, save as template. All right, I'll have to research that one. All right, I'll play with it and figure out how to poll. But if you can participate at least through the chat window, I'll just poll this way. So the first question that I posted in my poll was, did you start the derivation off correctly? And what I want to know is, did you at least begin with the sum of e to the tx times the right PMF? A simple y or n is fine. All right, so that's about 1/4 of the class, which is something. All right, and I know 2 of you at least got to the answer. Muku and Tony. Tim, Winnie, Aaron, were you also able to get the final MGF? In other words, after stating it, were you able to progress through and actually get an answer? Tim, do you mind sharing where you got stuck on? So not realizing that you could actually evaluate at x is 0 and also at x is 1, is that what you're saying, or was it something else? Okay, I mean, that's great. That's why I'm trying to work out kinks now and not on a quiz or something later on. Right? I assume many of the issues are probably similar, so hopefully this really clarified. But as you can see with the 3 different derivations that we did, that it wasn't, other than how you started, which is the sum of e to the tx times the PMF, the way you progress is different. One used the binomial formula trick. This one you just evaluated directly. Another one used 2 tricks, changing e to the tx to e to the t to the x power, and also your now favorites multiplied by the equivalent of 1 idea. So again, those are just tools for now that you've seen them a variety of times. You've got them under your belt. What would be advantageous is just to keep it in mind in case you might need it for the future. You probably won't need the binomial formula one, but the multiply 1, add 0, those are popular. Right, but that concludes applying this. using the MGF. To give you a little bit more practice before we go to the next topic, because we're fine on time, use the Bernoulli MGF that we now have in order to find the mean and variance for this distribution. So again, use this MGF, the one that we just derived for the Bernoulli distribution, to find mu and to find sigma squared. Again, I'll give a minute or so for you to work through that. Right, if you feel you have the mean, feel free to post that or say it. Miku, what did you get?
Not what other people got. So I got P for the mean.
That's right.
Oh.
And Tony, you are on the right track. Remember that after you get the first derivative, you have to evaluate at t equals 0. And you'll get the same thing that Miku just said. Same thing for none and constants. Yeah, so P and Q are constants, where Q is 1 minus P. I realize that you may not have the variance yet, but I'll start writing the solution to the mean part.
The mean part, are you using the moment or no?
Yeah, that's what I asked. I asked you to get the mean and the variance using the MGF for the Bernoulli, which means that you have to get the first and second moments. That is an ugly P. There we go.
But it's 0 and 1, yeah?
What?
You have to use 0 and 1, don't you?
For what?
Isn't that like the support or something?
Do you need to evaluate X?
I don't know. How do you get P?
It's all right there. P
Yeah.
is in the MGF, which is the box up on top. And so when you take the first derivative, you get PE to the T. And then when you evaluate at T is 0, you have P times E to the 0, E to the 0 is 1, and you're left with P. Anyone feel that they have the variance part? None. That is great. Yeah, good job. Anyone else manage to get what none got or the equivalent? Yeah, all right. Thanks, Tony. And Tim. All right, so let me go through and demonstrate that one. The variance requires, again, the second moment. And so that's going to be the derivative of the first moment. And we got just above that the first moment is PE to the T. So the derivative with respect to T of PE to the T is still PE to the T. So when we evaluate this at 0, we get P. But the variance is the second moment minus the square of the first moment. So that gives us P minus P squared, which is P times 1 minus P. And so it's more common to see your answer as P times Q. I'm not that picky. If you left it as P minus P squared, that's fine. So the Bernoulli distribution has a mean of P and a variance of P times Q. Thoughts, questions, concerns? All good. All right. So let's move on to the last topic then. This is the last distribution in the discrete chapter that you will learn formally. It's called the negative binomial distribution.
Wait, can you go back? Sorry, I didn't get the answer. Where'd you get the Q?
Q is 1 minus P.
Oh, yeah, that's right.
You have it all, Sydney, or like, can I go to the next page?
Okay.
Yeah?
Yeah.
Right, so the negative binomial distribution is going to have a form that looks like the binomial distribution. There is similarity. And here's your PMF. So it looks similar in the sense that you have a combination times a p to a power times the equivalent of a q to some other power. And so that's about, you know, how similar they are. But notice that whereas the binomial goes from 0 to n for x, the negative binomial goes from r to r upwards. And the reason for that is to understand when you use this distribution. So the negative binomial distribution is used when you want to know what is the probability that it takes X trials or subjects in order to see the rth success. And so this could be like, what is the probability that we need to speak to 20 people before we find 2 people that say that they plan on voting for Trump in this up and coming election? With that understanding, the rth success, or in the specific one I gave, the second success is that last person. So for that reason, you're choosing r minus 1 from the x minus 1, because that last one, that x value, is your final success. So that's why the combination term looks potentially unusual. It's because it ignores the very last observation, the xth one, because that is definitely a success. So again, here your x is discrete. It's a count corresponding to how many subjects you will need to sample or talk to or collect before you observe the rth one satisfying whatever criteria it is that you're looking for. So another example, and you'll see more as we progress through this, could be you'd use the negative binomial distribution if you want to know the probability of having to see 20 people before you see 7, or the 7th person wearing white. Or what's the probability of having 8 people go through a drive-through at Burger King before you see the first person to order a Burger King is the Whopper. Right? And so those scenarios are ones where you would use the negative binomial distribution in order to find the probability. All right, there is a special case, which is kind of on the bottom here. I'll highlight it. And this is when r is 1. When r is 1, it's still a negative binomial distribution, but because it simplifies really nicely to what I have there, it happens to be given a different name, which is the geometric distribution. So geometric is negative binomial when r is 1. Let's get to applying one or both of these. We'll see what's needed in each of the problems. So the first problem says, suppose that a basketball player can make a free throw 80% of the time. Assume that free throws are independent from one another. Let x represent the number of free throw attempts needed to make 10 shots. We want to compute the probability that x is 14. So what that P statement means is, what's the probability that it takes 14 shots in order to have seen 10 successful ones, which implies the 14th one is the 10th success. So let's implement the negative binomial in this case. We want the probability that x is 14, which means we need 13, choose 9. So there's, for the first 13 shots, any combination of 9 would satisfy, as long as the 14th one is a success, which is given by design. P is 80%, or 0.8, to the rth power, which is 10. So remember, r is the number of successes. So there's 10 successes, which means failure or missed shots is 20% of the time. And there are x minus 1, or sorry, x minus r, which is going to be 14 minus 10, or 4. So notice that the sum of the powers has to add up to your x. go ahead and compute this. And I will do it on my end too. And I got 0.1228. So there's about a 12.3% chance that we will have to wait 14 shots to see the 10th success. What's the probability, and this isn't asked in the problem, what's the probability that the person makes all of their first 10? So this is the minimum number of shots needed to observe 10 successful ones. Go ahead and see if you could put this together and get the answer. When you think you got an answer, feel free to post or call it out. Yeah, great job, Tony. So I wrote out most of it here. So you want to know the probability that it takes 10 shots in order to see 10 shots that are made, which of course implies that they make every shot up to the 10th one. So 9 choose 9 is the coefficient up front, the combination, which works out to be 1. You make 10 successes, so that's 0.8 to the 10, and you don't miss any, so that's 0.2 to the 0, which just simplifies to 0.8 to the 10, which is 0.1074. So for those of you that might play basketball, maybe you have an idea of, you know, your success rate, and now you're able to actually use this in order to say, ooh, what's the probability that I need 20 attempts in order to make half of them, or something like that. If you have an idea of how many baskets you typically make. But it's fun to play with. I wouldn't necessarily gamble on it, but can roast my friend. You sure can, too. All right, let's take a look at a non-sport one. And this is number 2. It says, some biology students were checking eye color in a large number of fruit flies. Suppose that 25% have white eyes and 75% have red eyes. Assume that eye color is independent across fruit flies. What is the probability that at least 4 flies have to be checked for eye color to observe a white-eyed fly? So the way this is written is that it's hard to come across a white-eyed fly, and the first one is red, the second one's red, the third one's red, the fourth one is a success, white. So this is implying the time to the first success, which is geometric. And the probability that x is 4, according to the geometric distribution, is going to be q to the third power times p. P is secretly to the first power. It's not usually written in. But again, the sum of the powers has to equal your x value. So q is failure. You've got fail, 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 success. So the next challenge is to figure out, well, which value do you use for q and which value do you use for p? What should the value of q be?
0.75.
Yeah, so fail would be a non-white, which is red in this case, red-eyed fly. So that's 0.75 to the 3, and p is going to be 1 minus that, which is 0.25. And you could do this in fractional form. I'll just compute it. And decimal form, it's about 0.1055. So geometric distribution, it's pretty nice. It's pretty simple and direct. There's no combination up front. It is just the number of trials to your first success, whatever success might be. There are a few more problems, but we've gone through 2. Any questions up to this point?
Wait, there's 2 separate answers for number 1, right?
No, there's one answer, and then I made up another question. So the first line is what the problem was actually asking. The second line in number 1 was one that I just posed to you guys just to give you practice.
Oh, wait, so probability of when p of x equals 14, are you determining the probability that you throw 14 times or something?
That it takes 14 attempts to have finally achieved 10 successful shots. Sydney, did that make sense? I'm not sure if silence means you got it or.
Oh, okay, yeah, I think so, yeah.
Let's look at this next one then. So we want to show that the geometric distribution is memoryless. And when we get the answer, you'll see why. So proving memorylessness is proving that the formula that I have below that, the conditional probability holds, that the probability of getting to k plus j, given that we are already at k, is just the probability of getting to j. So that's what we want to work through here. So remind me again what conditional probability, what that formula is. Probability of A given B is what?
Probability of A intersect B over the probability of B.
Mm-hmm. So this is the probability of X being greater than K plus J intersect or and. X is greater than K over the probability that X is greater than K. So that's just by definition. I'm working from the left side. So the conditional probability is equal to this statement that I wrote here already. Intersection is what they have in common, right? Intersection is what is in common. So I'm going to just make use of two number lines. And let's say that here's K, and that here's J. So X greater than K is going to be this region onwards. It continues right, you know, infinity. X greater than K plus J and this is approximate. Is going to be this region here. So what area, what region do they have in common? This bottom one represents X being greater than K, and this top one represents X being greater than K plus J. Where do their shadings overlap? Yeah, Tim, X greater than K plus J. So that means that this ratio is equivalent to the probability that X is greater than K plus J over the probability that X is greater than K. So that numerator simplifies through reasoning. It's from here that we actually apply the geometric distribution. So, geometric, you know what, let's actually explore the geometric distribution. And now m, of course, has to be an integer because this is discrete, which means that because geometric is discrete, this is the same as asking x greater than or equal to m plus 1. Because if it's greater than m, then it has to be the next integer up. And the distribution is q to the x minus 1 times p. So here x is going to be m plus 1 up to infinity. It goes on and on and on. So I want to figure out what this is. Let's go ahead and start evaluating. This is going to be q to the m times p. plus q to the m plus 1 times p plus q to the m plus 2 times p. And I trust you see a pattern. And to make our next step stand out, I'm going to factor a common component in each of these terms. Do we know what this infinite sum is equal to? We
1
did
over 1 minus r.
1 over 1 minus r. What is r in this case?
Isn't it a over 1 minus r?
But a is 1.
Well, how do you know it's 1?
Because a corresponds to the first term, and the first term is 1 in the sequence.
Wait, what is this again? This whole thing?
It's an infinite series.
I mean, like, what were we trying to solve up here?
Yes, no, and that's right, Q. What are we trying to solve? We are trying to figure out what the probability is of x being greater than some integer m using the geometric distribution. R is your common multiplier, which is Q. 1 times Q gets you Q. Q times Q gets you the next term, Q squared. Q squared times Q gets you the next term, Q cubed, and so forth. So this is 1 over 1 minus Q. But remember, Q is 1 minus P. And when you distribute that negative sign bottom, you get 1 minus 1 plus P. So this is 1 over P. Which means we have Q to the M times P times that infinite sum, which is equivalent to 1 over P. And lo and behold, we get Q to the M. Now this is great because this holds for any M integer. I'm going to go back up and make use of this fact that we just derived. So probability x being greater than m is Q to the M. In the problem we're working on, the numerator is the probability x is greater than k plus j. So m is k plus j, which means the numerator is Q to the k plus j power. And the denominator is Q to the k. The numerator is equivalent to Q to the k times Q to the j. Denominator stays the same. You'll notice Q to the k cancels out. And we get Q to the j. And now working backwards, Q to the j, where m is j, is the probability that x is greater than j. Which is exactly what we need to prove. So just to reiterate, I started with the left side here. The conditional probability is this statement. The numerator, I was able to deduce if the probability of x being greater than k plus j and greater than k, the only thing they have in common is x is greater than k plus j, which is how I got to the second step. And then deriving what I did at the bottom of this handout, I know that these greater than probabilities are q to the k plus j over q to the k, using the properties of exponents. I know q to the k plus j is q to the k times q to the j, which helps the q to the k's cancel out, and I'm left with q to the j power, which, working backwards, is the probability that x is greater than j. So that is memoryless, because it's saying if you want to know the probability of taking longer or going beyond k plus j, given that you're already at k, you don't need to care about k. You just need to know what's the probability of taking more than j turns, whatever it may be that you're looking at. So it's really neat to know which distributions are memoryless. This is the first one that we've come across that we derived, and that's how you would demonstrate it. Let's continue on with applications and look at number 4 here. It says, determine the probability of observing the 5th heads on the 10th flip of a fair coin. And so this is negative binomial, not geometric, because you don't want to see the first success, you want to see the 5th one. So here we want to know the let me change my color. We want the probability. Remember, x is the total number of tosses, so we take 10 flips to see the 5th success. So R is 5. And success is heads, which is 0.5. I know it's 0.5 because we're told it's a fair coin. And so now I could apply the formula. So this is going to be 9, choose 4, 0.5 to the 5 successes. 0.5 is, this corresponds to, it's awkward having the same thing for success and failure. This corresponds to failure, and that's going to be x minus r. So that is also 5, 10 minus 5. And this is what we want to calculate. And this comes out to 0.123. So about 12.3% chance, or that's the probability that it's going to require 10 flips to see 5 heads. All right, there is one more problem left and about 15 minutes to do it, so let's just see how it goes. In number 5, it says the probability that a company's workforce has no accidents in a given month is 0.7. Accidents from one month to another are independent, so whether June or May was a bad month doesn't impact whether June is also going to suck in terms of accidents. Part A asks, what is the probability that the 3rd month in a year is the 1st month to experience an accident? So here we want to know the probability to see the first event, meaning that this is a geometric scenario. So the probability that x is 3 months, means it's q to the 2nd power, because there's 2 months that fail according to our definition. Fail is no accidents. Success is an accident. This is an awkward one, but we want to know the first time we see an accident. And so here, 0.7 is no accident. So this is going to be 0.7 squared. And the probability of an accident is going to be 0.3. And this is about 14.7%. Part B, what are the chances that the company remains accident-free for at least 6 months? So this is the probability that X is greater than or equal to 6. Right? Accident-free for at least, so 6 or more. I'll give you a tip. This is the same as the probability that X is strictly greater than 5. Why did I do that? Why did I write it in this fashion? Or let me take a step back and ask a different question. Is this part B going to use negative binomial or geometric?
Negative binomial.
Why do you think?
Or I'm sorry, geometric.
Why, Miko?
Because if you remain accident-free for at least 6 months, then your 7th month, I guess, is the first time that you have an accident.
Well, at least implies 6 or more.
Okay. Oh, wait.
So you are right in terms of geometric. It's just the direction that you shifted the 6 to or from was flipped. And so it is geometric. The reason that I wrote it with respect to a strict greater than is because we just derived earlier what that probability is for a geometric distribution. We know the probability that X is greater than M is Q to the M power. So this, we know, is Q to the 5th power. Right? And Q is no accident, which is 0.7 to the 5th power. And that is 0.1681. So I made that adjustment from greater than or equal to just a strict greater than, so that I could use that shortcut, because we already derived, being that it's memoryless, we already derived what the probability that X greater than some M integer is. So it's a nice little shortcut. It'll work starting from scratch. You know, if we had let M be 5 here and you do all that summation, you'll still get to it. It's just we already did it once and it always holds regardless of what M is. So it's nice to keep that one in mind. And then part C, how likely is the company to have 2 accidents in a year? So now this one, is this still geometric? No. Is it negative binomial?
What's a negative binomial?
That is the distribution that this handout is about.
Oh, that's what it's called. Okay.
Mhm. Is part C requiring a negative binomial distribution or something else? And if it is a different distribution, which one? What is your hesitation with respect to saying it is or isn't negative binomial?
Because it's not necessarily saying that your like December is when you'll have the final success or the final or the second accident. So you could have it in like January, 2 accidents in January.
Yeah, so those 2 accidents, the second one doesn't have to be the 12th month. So it's not negative binomial. Which distribution should you use then?
Wait, geometric distribution is a special case?
Mm-hmm.
So it is a negative binomial?
No, I said part C is not negative binomial.
So it's not geometric distribution either then?
Because geometric would be asking the probability of the first event occurring, whereas here we're not looking for the first, we're looking at 2 events. Yeah, non, that's perfect. Just a regular binomial distribution. You've got months are independent from one another, that was told earlier. You know the probability of success, probability of no accident or probability of accident. And it doesn't matter which months those 2 accidents occur. You know that n corresponds to number of months, and you're looking at a year, so you know that's 12. So n is 12. We want to know the probability that x is 2. So x corresponds to the number of accidents, which means our little p is the probability of having an accident, which is 0.3. And so the binomial distribution says 12, choose 2, p, which is 0.3 to the x, which is 2, 0.7 to the 10, so 2 months with an accident, 10 months without an accident. And I'm getting 0.1678.
Wait, you're looking at like 2 successes instead of 1. Is that why it's just a regular binomial?
No, it's regular binomial because the way it's written, that second success or the second accident doesn't have to be in the 12th month. So it doesn't have to occur at the end of the year.
Wait, but it doesn't have to occur at, wait, so it has to occur at the end of the year?
No, it could have been January and February, and then the next 10 months they were accident free.
No, I mean, in order for it to be a negative binomial, it has to occur at the end of the year.
Oh yeah, okay. So for it to be a negative binomial, the last success, the rth success, or in this case, the second accident, would have to be in the last month, the last observation.
I thought you were just observing one success, maybe not the first one, but rth success, maybe just the second or something, or third.
No.
But it's just only one, but you're asking for 2 accidents. So that's why I thought it wasn't the negative binomial because of that.
No, here's the difference.
Wait, so negative binomial, you're looking for more, you can look for more than one success?
All right, hold on.
Can't see your screen anymore.
Yeah,
Oh, okay.
I'll yell at my mom later. She kicked this off.
Wait, so negative binomial doesn't mean you're searching for just one success. It could be multiple.
Delete. Here. All right, so think about the difference in the phrasing of C and D. And this 0.7 is no accident. This is.
Wait, so D is negative binomial?
Mm-hmm. And you get very different answers. So it's way more likely for them to have 2 accidents in a year, but it's highly unlikely for them to have to wait 12 months to have the second accident. And that's it. That concludes the discrete distribution chapter. So we've gone through 5 or 6 different distributions, many well-known ones. You've learned how to compute or derive expected value and moments, and use a moment generating function, even find an MGF. And so there's been a lot accomplished in this chapter. What's coming next in the course is we're going to go through the whole process over again, but for continuous distributions, what that really means is all the distributions that we've been using, I tend to write a summation symbol for, but with a continuous case, as you learned in Calc 1, the summation is replaced by an integral. So that's really the fundamental change, is that all of those summation signs that popped up are going to suddenly become integration symbols. and we are going to learn how to get expected value and MGFs when you have continuous functions. So that is how we're going to be spending the next week or two, and then I'll give you an update when we're about to end that chapter too. It should be on the calendar, but just to remind everyone, you have a quiz this Saturday, and then the next quiz is Friday next week. July 4th is Saturday, and there's a quiz Sunday also. So there's 3 quizzes coming up within 10 days. So just keep that in mind. It's all discrete related, so everything that we cover next week, it's not going to be on these quizzes. I just didn't want to fall too far behind in terms of the quizzes and the lecture material. So there may be another week where I have to squeeze 2 quizzes in, but I didn't want to delay too long from trying to catch up on that front. Other than that, I think it's been going great. Thank you for the participation, and that's all I'm going to be presenting for today. I will see you guys on Sunday.
Can you go back to question 4?
Sure. If any of you want to hang out, that's fine. Otherwise, I will talk to you later. Bye.
I have one quick.
Oh yeah, quick question.
What time